Hello and welcome to this Chemistry World webinar. I'm Natalie Starkey, Chemistry World's science media producer, and I'm here for about the next hour to discuss AI and automation in chemistry laboratories. This webinar is running alongside our most recent Chemistry World special issue magazine and online collection on AI and automation in chemistry. And there are a number of articles that you can read following this webinar if you want to delve into the topic in more detail. These can be found on the Chemistry World website, and we'll post the link to the collection in the chat for some further reading. Now, lab automation, at a basic level anyway, is fairly commonplace in chemistry laboratories these days, and automated routines are certainly capable of carrying out relatively straightforward tasks ad nauseum, freeing up a scientist's time to a certain extent. But you might question if robotic lab assistants can cope with the wide range of duties required for all laboratory research, much of which demands adaptive and analytical skills. And the question is, are you just wanting to do your work faster, or are you actually looking to completely overhaul your experimental setup and optimize your workflow? Throughout this hour, you'll meet three chemists, Nessa Carson, Andy Cooper, and Felix Street-Kalthoff, who I will now invite to turn on their cameras so we can welcome them here today. There we go, we have all of them. So welcome to all of you. Thank you so much for joining us. These scientists have successfully incorporated lab automation into their research, and we'll be finding out how and why they decided to do so, as well as learning about the challenges they might have experienced along the way. Now, this session is interactive, allowing you to ask questions about any aspects of what's being covered, or you can also share your own ideas for how you've achieved similar success in your own laboratory. You're able to ask questions on the GoToWebinar platform at any time during the hour, even during the presentations, and our presenters will be able to answer your questions in the live Q&A in the second half of the webinar. As a quick explainer, on GoToWebinar, there's usually a panel down one side of the screen, although this might be different depending on which platform you're using, especially if you've joined us via a tablet or a phone. Now, somewhere on that panel, there's a questions box, so feel free to put your questions in there at any time. I will now introduce our three guests in more detail. So we'll start with Nessa Carson, who we have with us, and she is the digital champion in early chemical development at AstraZeneca, where she focuses on making life easier for chemists and analysts with data management and accessible digital tools. Nessa also maintains a website of useful chemistry resources, supersciencegirl.co.uk, which again, we'll share the link for in the chat. Nessa has also recently written a feature for Chemistry World focusing on how to automate your lab, which again, we'll share a link to in the chat in case you'd like to read more after the webinar. You can find that on the Chemistry World website. We also have Professor Andy Cooper, who's based at the University of Liverpool. He's the director of the Leverhulme Research Centre for Functional Materials Design and academic director of the Materials Innovation Factory. And his main research interests are organic materials, supramolecular chemistry, and materials for energy production and molecular separation. This is underpinned by a strong technical interest in high throughput methods and robotics. And last but not least, we have Felix Street-Kalthoff, who's currently a postdoctoral fellow at the University of Toronto, where his research is focused on the integration of lab automation and artificial intelligence to realise self-driving laboratories for accelerated materials discovery. So just to let you know, a link of a recording of today's webinar will be sent out to everyone who's registered. So please don't worry if you miss anything, as you can always go back and watch again. Now, just before we get started, and we're going to hear from Nessa first, I'd like to actually just put a poll question out to everyone that's watching, and it's going to come up on the screen in just a minute. We're really interested to hear from you about your experience with lab automation, because we don't know who we've got in our audience today, and it's lovely to hear from you and kind of know what experience you've had. So please feel free to click on the option that best describes you. If there isn't an option, I'm very sorry. We obviously missed out one of an option. So just don't worry about doing the poll if there isn't anything that describes your experience. But if there is, please click on something. Basically, how much experience have you had of lab automation? You might be very experienced. You might work in a fully automated lab like some of our speakers today. But equally, like myself, you may have no experience of lab automation, but you might be looking to incorporate it into your work. Just going to give you a little bit of time. My timer is telling me you've had nearly a minute, so I'm going to let you have that full minute to put your answers in. I can see quite a few people have already put their answers in. Actually, over 60% of you. Wow, that's really good. Thank you. Thank you for getting involved. Okay, I think we'll end the poll there. I think most people have actually managed to vote, and I hope that we can get the answers up on screen. There we go. So quite a mixed bag today. We have a few very experienced people. I'm really interested to hear from those people. Maybe you can put some questions in the chat to explain what you've done, and maybe when you've heard the speakers you can get involved and share your experiences. And we've got some people like myself who have no experience here, and a few people in the middle. So I'm really excited that we've got that range, and I know that you're probably all working in very different areas anyway, so this is part of the joy of these webinars. We get to share loads of different science and loads of different ideas. So you'll be hearing from our speakers, and then we'll move on to the Q&A question session at the end. So please start putting in your questions at any time, and I'll put those to the speakers at the end. So without further ado, because I've spoken for long enough, I'd like to welcome Nessa to speak first. So if Nessa, you'd like to turn on your camera and audio and share your presentation, I will be quiet now and hand over to you. Thank you.
Cool. Okay, hopefully you're seeing the right slide there.
Yep, that's working.
Just like triple checking, because you never know. Cool. Okay, thanks so much for that introduction. Yeah, well, that sounds really exciting. So we've got a good mix of experience levels here. So do not worry if you've not worked with lab automation before. I'm hopefully not going to go into loads and loads of detail without giving you the background for it first. So I thought I'd start off by pointing out where we use automation at AstraZeneca. So I guess this is the kind of life cycle of how long it takes to make a drug. So at least in terms of chemistry. So we're starting off here right at the very beginning of the discovery process, where we have a super fancy lab over in Sweden called the iLab. So they're doing a lot of parallel chemistry, i.e. they're doing many different reactions at once, making different substrates, so making really large libraries. Moving on to discovery chemistry, so that's kind of medchem, maybe starting to scale up, maybe scaling up intermediates, but you certainly don't know which exact substance you're going to be developing as a drug yet. Early chemical development is where I am, so that's early process chemistry, moving into late process chemistry, moving into everything on the market. And what I really wanted to point out here is that right the way from here to late chemical development for sure, and sometimes beyond, sometimes post-marketing, is where we use automation. Of course, also before this and during particularly discovery, there's also discovery biology. So that's very similar, kind of, in terms of automation, except that in chemistry, we need to use a lot of reactive compounds. We need to use heterogeneous mixtures. We need to stir them. You know, sometimes you're dealing with very high temperatures and acids like corrosive compounds, things that will certainly react with plastic, lots of solvents. So even though robots are really well developed for biology, they're actually less so for chemistry because of those additional challenges. We're not just pipetting DMSO and ethanol most of the time. So why are we using this so much? Well, the main thing that I've focused on in my career, and something that we do a lot of at AZ, is high throughput experimentation, or HTE. You'll see it called quite a lot. Sometimes HTS for high throughput screening, but that tends to be more of a biology term. Sometimes they're a bit interchangeable, so it gets a bit confusing. It's not really kind of just screening, so that's why we typically call it HTE. So yes, we use fancy robots like the ones you kind of can't really see here because they're in glove boxes, but this is one of the labs where I work, absolutely filled with glove boxes. These glove boxes are filled with beautiful robots. And here's an example of one of them, just looking at the deck of an Unchained Labs robot. So you've got syringes for liquid dispensing. You can incorporate all kinds of things, balances, even solid dispensing. Capping, uncapping, all sorts of things that you might want to do, heating, stirring, cooling, possibly even photochemistry, things like that, pressure reactions, anything that you might want to do in a kind of standard chemistry lab. It's just that now there's a lot of them and they're automated. But they don't have to be super fancy robots like these. So actually we use automation all over the place. NMR, autosampler carousels, automated flash chromatography, that sort of thing. I mean, even technically speaking, then a stir a hot plate is automation, right? So rather than having to stir things all the time, I'm going to use discovery chemistry as an example. Even though I work in process chemistry, like I kind of had this slide handy, so I thought this would be quite nice to share. So we talk a lot about the DMTA cycle for discovery chemistry, medchem, and that's just design, make, test, analyze. You design the compounds. Here we can use I guess parallel synthesis, we can use software automation, make the compounds. I guess that's the parallel synthesis part. Maybe I should have that over here. Along with having to optimize the reactions, because if they don't work that well in the first place, you know, you're going to need something that works decently. So reaction optimization is absolutely key here. Testing is bioassays, again, those biology robots that maybe don't work so well for chemists. And analysis, again, software automation. This is analyzing the biotesting results, and that feeds right back into the cycle where you're designing more compounds again. So I'm going to talk very quickly about what I've done with high throughput reaction optimization, so HT, high throughput experimentation again. So we use this in both discovery and process. We use this all over the place in chemistry. We use it in formulation and things like that. But reaction optimization specifically, what it isn't is trying random conditions. Like, you can do that. It's not really about trying just everything, though. Just throw all the ligands you have at something and hope that one will work. You can do that, but and like sometimes if you're desperate, you'll do that. Typically, I guess that's quite, you know, quite low tech in a way, even if you're doing it with fancy robots. So typically you'll have an experimental design that takes trained scientists, particularly people who are really used to doing HTE, to design that experiment. Not particularly similar to high throughput bioassays, as I say. And reaction optimization is not library synthesis, so it's not the same as making loads and loads of compounds at the same time. It's usually making one compound or a few compounds, but you're trying a bunch of different conditions. Honestly, it will work with basically any chemistry. So if you're doing reaction optimization, I'm going to use that as an example because that's what I've done for most of my career. Here is an example that I quite often show when I'm speaking to university students, you know, various years. Some people haven't come across that many kinds of chemistry yet. So here we have a palladium catalyst. It's going to be a catalyst at some point. And because we're using palladium, it's got these triphenylphosphine ligands attached. Those are changing the environments around palladium. So this is different than just using palladium chloride, right? And whatever phosphine ligands or whatever ligands you choose to attach to the palladium affect the reaction in sometimes very, very subtle ways. So here's another example of a ligand. It looks very similar to the triphenylphosphines, except now they're tied back. So this is DPPE as a ligand. And if you look at these two, admittedly not amazing, computationally minimized structures, you can see that actually, yeah, there's a bit of change in the geometry here. It's not just about the sterics, of course, it's about the electronics and all sorts of different aspects of what those phosphines do to palladium. I'm giving this as an example because cross-coupling is really important in high throughput reaction optimization, and you can do very, very many types of chemistry with it. So here's just an example of aminating an aryl bromide. So yeah, there's a lot you can do with that. What I do want to show right now is I love this work. So this is not by me. This is some work by GSK researchers that they published in Nature Catalysis as a perspective a few years back. So what they're doing, and I deliberately haven't shown the reaction, I'm kind of trying to make the point that the reaction doesn't matter. So even if you don't know what this kind of reaction is all about, doesn't matter. This is a cross coupling, like in the previous slide. And here are little pictures of all the ligands they've used. They're all phosphines. They're all very different kinds of phosphines. And the researchers have tested all of these with a base that they chose to be disopropylethylamine, DIPEA, and a solvent they just chose acetonitrile. So they've tried all of these ligands kind of in little vials next to each other, I guess. And they've seen that there's a big variety of yields here. I won't really go into any particular details, but basically a lot of them didn't work. If you look closely, you'll see the monophosphines tended not to work so well. And then there are some that did work quite nicely. So DCEphos has given us a 61% yield. Xanthos has given us an 81% yield. So there we are. Xanthos is the winner. And then the researchers decided, okay, we've figured out our ligand. We're now going to try out some different bases. So we've got potassium carbonate and we've got potassium acetate there. We're also going to try one different solvent, so that's toluene. And they actually tried 6 combinations here. Of those, it's still the xanthos, disopropylethylamine, and acetonitrile that's the best. But then they say classical screening gives a local maximum, not a fully optimized system. So how would you fully optimize that system? Well, you can try every single combination. There are clever statistical methods where you don't need to try every combination. Here I'm going to talk about every combination because it's easy to talk about and understand what's going on. So here are the conditions that we optimized before, which is basically by going down this line, and we can see that there's our 81% yield. But if you look at the rest of the condition space, there are 8 better sets of conditions here, and actually the best is basically quantitative yield of the desired product from DCPE, totally different ligand, toluene as the solvent, and potassium carbonate as the base. So that's completely different than the 81% that we had before. Really, I'm saying this because it's really important, even though you see in the literature this one factor at a time thing constantly, it's really important to explore chemical space, and that's the mindset change that you do when you're working with high throughput reaction optimization, or in fact library synthesis, in which case I guess it's chemical space rather than condition space. The other thing is you can't do 1096 well plates a week without automation. Okay, not everybody wants to do 1096 well plates a week. You've got to start somewhere. Actually, that is where I started, and it was really cool. But even if you don't have a multi-million-pound fleet of fancy robotics, there are ways you can get started doing things like this, exploring chemical space in a more sensible manner than this kind of picking your ligand and only then deciding on base and solvents. So a 24 well or 48 well plate, it won't cover as much chemical space as this. There's 96 on this slide. But it can be run on an ordinary hot plate, ordinary stirrer hot plate. You can use multi-channel pipettes. You can use a single channel pipettes, particularly for a 24 well plate. So yeah, the more wells you have, the fancier equipment you need. But also, you know, if you go above 96, there are kind of limitations in how you have to run it. So actually, probably if you're getting started and your budget's not quite yet stretching to multi-million-pound robots, then 24 well or 48 well plates are probably the way to go. You just have to be prepared for that mindset change as well. Okay, well, that's basically it for me. So everything I talked about so far is absolutely nowhere near the only things that you can do with automation. So Andy and Felix are going to talk about some very different things, because they do quite different things to me, also using robots. And yes, you don't have to code, but I guess all I'm saying is that software automation is also incredibly important.
Thank you so much, Nessa. That was a great introduction, and I love that we've kind of covered a bit about how we get into this, because I think as you've seen from the poll, we've got a lot of people in the room who haven't maybe done any of this kind of work before, and I imagine it's a bit daunting kind of figuring out where to start, and actually that's been really interesting to see. I think we're now welcoming Andy back, and we're going to go a little bit to the other end of the scale. Having seen a little preview of his presentation, I feel like we're definitely now going to push the lab automation the other way and see some of the other amazing work that Andy's doing. So Andy, if you want to share your slides now. Brilliant. I will mute myself and let you kick off. Thank you.
Okay, well, thank you. And thanks, Nessa, for that introduction. It leads nicely into what I'm going to say. I'm going to say something about our work using mobile robots for automation. But before that, just to say, for those who are kind of new to the area, there are a variety of different methods out there now. Nessa mentioned Unchained Labs, which is a commercial solution. ChemSpeed is another one. ChemSpeed Technologies has been a provider in this area for some years. And there's various academic activities too. The Cronin Group in Glasgow have produced what they call the Computer, which is this autonomous synthesis platform. This is some work from MIT and the Jensen Group. Produced a different kind of configuration, and I think we might hear from Felix about work going on in Canada and UBC and Toronto, materials acceleration platforms. So there's a variety of different hardware available, and actually you can string this together in very sophisticated ways. So here is the Stratios Cloud Lab in California. This is like a production line for drug discovery effectively. So it's a very large lab integrating ChemSpeed hardware and other hardware. And it's effectively a lab on tracks. So it runs around a very large warehouse-like facility. And it's pretty impressive. But there are some limitations. For one thing, you know, if you don't have $100 million, it's hard to build one of these. And also, it is really bespoke to a problem. So we kind of got interested in more flexible ways or different ways to do automation. And the basic idea was, if you look at the global scientific instrument market, that's worth something like $55 billion or thereabouts. And nearly all of those instruments are built to be used by humans, not robots. So the idea we had was to try to automate the researcher rather than the instruments. And we came at this partly from being materials chemists, where some of the instruments we use are physically large, you know, they're not so amenable to hard integration. So we built this system which got dubbed the robo-chemist or robotic chemist. And this is an autonomous mobile platform that can work in a relatively conventional lab. And as you'll see, use equipment rather like a human with little or sometimes no modification. And it can think or reason or at least optimize in high dimensional space. So it can also perform its own experiments autonomously. So this is the system. It got featured on the BBC News in 2020. So you can see here it is in the lab moving around doing experiments using instruments essentially by itself. And the news item highlighted the social distancing skills because this was in the middle of the lockdown, first lockdown. So what does it do? Well, it does the operations that are relevant to, in this case, heterogeneous catalysis. So solid dispensing, liquid dispensing. This is a photochemical reaction, so it does photocatalysis. And here measurement, and the measurement here is GC. So that's a conventional GCMS platform, and we haven't modified it at all. So the robot drives up, presses the button and runs it. So there's no physical modification here. Could be HPLC, could be benchtop NMR or other things. So this gives an example of the system actually running an experiment. So this little video condenses 2 days into just 60 seconds. You can see it's Friday night in 2019, and it's carrying out a photocatalysis experiment. And this is the number of experiments done in the box down here. So the system does 16 experiments in a batch, as a rack, 16 experiments. So for context, we used to do these things by hand with a manual injection GC, and we'd do maybe 1 or 2 a day. So you can get a sense of how much faster this is. So every time it increments in 16, it's on 64 experiments. You can see the time here. So this is working 24/7 with small breaks to recharge the battery. And you can see work-life balance here. There are absolutely no students in the lab, so just the robot. Well, it is midnight, so you wouldn't expect students in the lab. After 2 days, it's done 192 experiments. So if you work that out, it's about 2,000 times faster in terms of human input. So here's a real experiment that we published in 2020, and I don't have time to go through the chemistry, but it's a photocatalysis experiment, and we had 6 independent hypotheses. And what we did is we basically broke the first law of experimental design, which is change one thing at a time. The robot changes everything at once, and it uses an algorithm and a technique called Bayesian optimization, which Felix may mention, I think, in his talk, to optimize in this high dimensional space. So there are 10 dimensions, and if you work it out, there are almost 100 million possible combinations of these components in the catalyst formulation. So what you do in practice is you load up the solids and the liquids into the relevant dispensers, and you set the thing running. This plot shows the catalyst activity as a function of sample number or experiment number. And this radial plot shows the experimental variable space that's being sampled at the time. So we hit the run button, and it runs over 8 days by itself and does something like 700 experiments. You can see the starting catalyst concentration in black squares here, and you can see very quickly it finds solutions which are much better. So the ultimate catalyst activity is about 6 times higher than the baseline. We actually do start with random points initially, but very quickly it becomes non-random and selects some subset of the components. So it finds a new catalyst formulation by itself. That can work in 10-dimensional space. It could probably work in 15-dimensional space. If you had a much higher dimensional space, you'd need a different approach. And if you work out the time saving, this is not all about time savings, I should say, but the manual approach was kind of 1 sample a day or maybe 2 samples a day. Then in 2018, we published a semi-automated approach where we managed to accelerate this a lot. So 1,000 samples would take not 1,000 days, but 5 days. But something to note is that this autonomous system is 10 times faster than the automated system. The reason for that is if you look at the plot at the bottom, it takes about half a day to set the thing up, and then you simply leave it. So the human input is in red here, I should say. So the human time, not the absolute time, because that's not a factor of 10, but the human input time is accelerated by a factor of 10 compared to the automated methods. Now, it's not to say these are kind of separate universes, and you can join these things up. So this is some work we haven't published yet, but this is a ChemSpeed synthesizer. So the idea is a robot using a robot here. So the synthesis is done on the ChemSpeed platform, then the robot is used to interface with that. You can see it drives up to the ChemSpeed robot. It's going to take some samples from the ChemSpeed robot, and in this case, it's going to take those samples to LCMS instrument, which is here. But that could be any instrument, and it could, in principle, be in an adjoining lab if you had a way to open the door. So this is a highly modular system. You can see here in the background is a benchtop NMR. But essentially anything you can have in your lab in principle can be automated this way, because the robot is designed to have roughly humanoid dimensions and reach. So it can access things at benchtop height. I won't talk about it today, but this purely autonomous approach we think runs out of steam in many cases. So we're now looking at ways to better fold in human judgment in real time into these optimizations, because autonomous searches are great, but actually human insight and human input can be much more effective than AI by itself, we believe. And a couple of drivers here, and these were taken from a review that was not written by me, but was written again by Canadian colleagues. A couple of drivers. Robot costs are coming down quite sharply. and the number of papers in this area going up quite sharply, and the two, I believe, are interrelated. So something about this mobile approach is modularity and flexibility, but actually many of these approaches are modular and flexible, not only these mobile robots, and I think that's going to lead to a sort of real explosion of ideas. And you can implement this in your own labs. It's certainly not multi-million-pound stuff, to take Nessa's point. You know, the cost of one of these mobile robots is actually less than the cost of a high-end LC or something, which most labs have. And you can see the idea is beginning to spread. This is an implementation in China, also a photocatalysis implementation. This came out last year, where they built the same sort of platform, but with entirely different hardware. So I think we're going to see more of these systems in the future. Brief plug for our spin-out company, Giru. We hope to have the first commercial system of this type installed later this year. And thank you to the people who did the work. Thank you.
Thank you so much. That's amazing. Just the numbers that you're talking about in terms of, you know, how much more the robots can do is phenomenal. Like it just blows my mind a bit, you know, where you said you could do 1 to 2 experiments in a day, and then they're looking at, you know, however many it was, 60 or more. It's just amazing. It's really opening up the field, isn't it? And it's just amazing to learn about all this different stuff that's going on. So thank you so much. That was a great introduction. We've got some questions coming in, so people are very engaged with what they're hearing about, which is great. So please do keep your questions coming. I will be putting those to our panelists at the end. So we're going to hear from Felix next, and then we'll be coming on to the questions. So you've got lots of time to think. Thanks so much, Andy. We'll come back to you soon. But yeah, Felix, if you'd like to turn your camera, thank you very much. And if you'd like to find your presentation to share, we'll be ready to hear from you to add another aspect to this lab automation business. And then, yeah, we'll welcome the others back. Right, that's all on screen for me. Thank you.
All right, thank you so much for the kind intro, and I'm really happy to be here today. And yeah, kind of following up a bit on the spirit of kind of what it takes to get into lab automation to get started, I want to talk about automation from a bit of a different perspective, about the actual chemistry that we've been doing, but rather on how we can actually integrate robots into our workflows and what it takes to do that. And kind of before doing that, in the spirit of getting into lab automation, let me give you a quick intro about myself and how I actually got into lab automation. So I am by training a traditional organic chemist, studied chemistry at the University of Münster in Germany, did a research stay in the US where I did classical experimental organic chemistry, moved back to Germany, started my PhD with Frank Glorius at the University of Münster, where I mainly, again, worked experimentally in method development and homogeneous photocatalysis, essentially not much of robotics and automation involved, but started to develop an interest into, let's say, computational modeling and machine learning for reactivity prediction. And kind of with that motivation and that idea in mind, I moved across the Atlantic again to join Alan Aspergusik's lab, where I'm currently working as a postdoc at the University of Toronto. And this is like really the first time I really worked hardcore with robotics, and kind of the research goal that we're focusing on is kind of the integration of AI and automation for self-driving labs. So what's the idea of a self-driving lab? And I mean, Andy already had like a beautiful intro into like what the concept behind that is. So, I mean, traditionally what we do is we do science in loops. So meaning that we kind of formulate a hypothesis, design an experiment to prove or validate this hypothesis, perform the experiment, evaluate the data, and then update our hypothesis based on the data that we get. And the goal of kind of self-driving labs is to really accelerate this cycle by, on the one hand, integrating AI into the experiment planning part. I'm not going to talk about that in too much detail today. And then on the other hand, really streamline and accelerate and increase the throughput of experiment execution by integrating robotics. And really running this closed loop in an automated fashion, as Andy showed earlier, is kind of what we think about of self-driving labs. And yeah, today I'm going to focus on like the right-hand side, so the actual robots and the experiment execution that goes along with it. And I mean, if we think about like getting into it, many of us who have worked in even what we would consider a conventional research lab have worked a lot with automation. Nessa pointed that out, because in the end, if we work with a GCMS, if we work with an NMR, with an autosampler, with a spectrometer, all of those devices are kind of automated platforms already. And automation kind of meaning that it performs a task or a sequence of tasks without actually needing a human to intervene at that point. And that's in the end what lab automation is about. Finding more and more of those workflows that we can actually have a robotic platform run without us as a human intervening. And if we think about kind of where do we get these platforms from? How do we actually get started? That's a bit of a question that I also asked myself. And so I want to quickly talk about that a bit. And I mean, there's kind of two solutions to that. The one is we take a commercial robotic platform and buy whatever is out there on the market. Or the other option is we build it ourselves. And of course, depending on the complexity of the task and how much is out there in the literature or like on the market, there might be not an option but taking a commercial platform, because we won't have the time or the expertise to actually implement something by ourselves. And then also the second big advantage of commercial robotic platforms is that they are rather robust. They are designed and commercialized and extremely well tested for these specific tasks, so they can usually do them quite robust. But as mentioned earlier, many robotic systems come with pretty high prices. So there's like a cost barrier to that could sometimes kind of be an incentive of developing a system by yourself. Especially then when you need something that is like very fine-tuned and very narrow for a specific task that a commercial robot might not be able to do. And then there are two aspects that I want to talk about in a bit further detail that actually are a major challenge with commercial robotic platforms when we want to implement them into lab workflows, which is on the one hand the control software and on the other side the data readout. Because many commercial platforms come with proprietary software and proprietary data readout. And that's a problem if we want to include them into higher level workflows and higher level routines. So in the end, if we want to really include a robotic platform, may it be a dosing station for solid dispensing, for liquid dispensing, may it be an HPLC, may it be a characterization platform for materials. What we in the end want, on the one side, we want to give the robot an input to say, okay, do this task right now. And then it does it, and we want to get the data out. And the data that we want to get out in the end, what we need is we need data that kind of follows the standards of fair data, meaning that it's findable, accessible, but especially interoperable and reusable. So we must be able to access the data to process it outside of the robot. And that's kind of a major challenge that often comes along with commercial platforms, which is, for example, why we in our lab have spent quite a bit of time writing wrappers around commercial software so that we can use the robots in the flexible and modular way that we actually want to use them. Let me give one brief example of a point where we actually implemented our own home-built system for a specific task where there wasn't a good commercial system available, which is in the context of optoelectronic materials, we need a lot of optical characterization of materials. So what we have built in our lab is a fully automated end-to-end workflow to characterize samples in solution optically, where we put a sample in and then automatically measure absorption spectra, so classical UV-Vis spectra, emission spectra, but also measure the quantum yield and, in time-resolved emission, the excited state lifetimes of our compounds, which are extremely important for our analyses, for example, when we work with laser or OLED materials. I mean, such a system from the outside does not look very spectacular because it's in the end a whole mess of tubes and wires and black boxes. But more importantly, we have like fully automated this system and fully developed it ourselves. So we have all the requirements that we need from the software side to really integrate them into our higher level workflows. So we have, in this case, a Python API where we can perfectly control that robot to do exactly the task that we want at any given time with all the details that we need, since we developed the system ourselves. And we also get all the data that we want out in in our case, Python format that we can use, that we can transform, that we can save in any format we want, and kind of really fully integrate that into our workflow without having to deal with proprietary data formats or all that part. So we really now have a robot or one robotic platform that we can actually put into such a self-driving lab. Now, Andy already beautifully demonstrated that usually like a workflow takes more than one robot and more than one platform. So in the end, we might want to synthesize a material, purify it, and then characterize it. And for all of that, if we want to have a full closed loop discovery cycle, we need robots that can do that. So we kind of need, for each robot, we need an interface to some kind of operating system for our self-driving lab that can send commands, that can kind of say, okay, now do this analysis. We need to always know about the instrument status, in which status the instrument is right now, and which capabilities it has. And we need to query back the experimental data. And then kind of queue multiple robotic platforms together and operate them kind of through a single operating system. And I mean, that idea of like a central operating system that combines multiple devices and has them work together to achieve a certain goal is like nothing that chemistry labs have invented. That has been out there for quite a long time. The concept has been called the Internet of Things, and essentially a kind of robotic chemistry lab that puts together multiple robots and multiple workflows. It's not that far away from the ideas from the Internet of Things, where we have a central operating system that stores all the data, that knows what robot can do what robot has which status, what robot is doing which experiment at the current point, and then allocates experimental resources and kind of drives this overall discovery workflow. This operating system is then also directly hooked up to the AI algorithm that helps us to plan experiments, and by that kind of enables such closed loop discovery workflows. We have developed such operating systems in our lab, for example, the ChemOS platform that I cited here, but I don't have to have time to go into too much detail about. But yeah, these are kind of, in my view, the essential part of actually running automated workflows in labs, and probably the different robotic labs and the different platforms like require these central operating systems to run a lab. Let me finish by giving you a quick sneak preview of how we are currently extending this idea of central operating systems. Because what if we actually want to leverage capacities of multiple labs, or of multiple robots all over the world, which can potentially do the same or similar tasks, but with slightly different flavors or different throughputs or different reagents? How would we bring all of that together? And now it really goes into the direction of an Internet of Things. And we now have developed a central operating system for delocalized materials, or for delocalized discovery campaigns in general, where we have a central cloud-based operating system that consists of a database that knows all the experimental data that has been generated at all different sites, but it also knows the status of the robots at the different sites, also which reagents they have available, so that it can then efficiently allocate experimental resources based on the availability and capacities of the different robots, and kind of enable a single asynchronous delocalized discovery cycle, but with the actual experimentation delocalized over multiple places. And we're currently running an experimental campaign where we really do materials discovery with experiments all across the world. So the places of the robots are actually like roughly estimated on that slide. And this is something that I'm really excited about when it comes to automation and the power of robots for chemistry. How do we actually kind of democratize experimentation and kind of make maximum use of the experimental capacities that we potentially have available, without different labs running duplicate experiments, or kind of doing things that would not be necessary if we could potentially centrally coordinate everything. I want to finish off, of course, with the most important slide, because automation is an extremely interdisciplinary topic. I'm very happy that I have the pleasure to work in an extremely interdisciplinary team between chemists, physicists, computer scientists, engineers, and so on. Because I mean, automation is a challenging but extremely exciting field to work in, and I'm looking forward to kind of what the future holds in that field, and also looking forward to discussing with you and the other panelists about future directions and ideas in terms of lab automation. Thank you.
Thank you so much, Felix. Goodness me, we've covered a lot in this webinar already. If I'll welcome everyone to turn on their cameras again. So Andy and Nessa and Felix, feel free to keep yours on. And yeah, microphone's on. We've got loads of questions and we have about 15 minutes. So we'll see. We'll try and do some quick fire questions, maybe, because we've got a lot to get through. I'm going to start with quite a good one, actually. And it's kind of aimed at all of you, but probably Andy most. What kind of skill set are you looking for when recruiting students and postdocs to your lab? And I'll probably add on to that technicians too, because I imagine, you know, it's a whole lab effort, as Felix has just mentioned, in terms of the teamwork. Are we looking for something different to what you used to look for before lab automation kind of existed?
Yeah, I could start, I guess, briefly. When we started, we were doing it all using basically skills that chemists had, but recently we've got teams of computer scientists and roboticists involved as well, and that has really made a massive difference to what we can do. So I mean, you can definitely go a long way with chemists though, and I would say it doesn't require that, but it certainly helps.
Do you think we're losing anything in automating work? Are we losing those basic chemistry skills that, you know, we take for granted masters and PhD students learn, and even undergrads? Do you think there's going to be a problem in the future that people aren't understanding what they're doing? It's just the robot's done the work and you've got the data out at the end. And that's to any of you, really.
Well, I would say no. I would say we're losing weighing and pipetting, but I'll pass it over to Felix and Nessa.
Yeah, I can't emphasize that point more. I think, like, yes, in the chemistry education, we can't completely lose the kind of classical chemistry skills, because it's important that we still know kind of what the robot is doing and what kind of experiment they're doing, what are kind of the critical factors in there. But kind of during a PhD, I think there's not a big point in weighing in tens of thousands of catalysts and reactants. So it's kind of really accelerating our workflows and giving us as chemists kind of the chance to focus more on actually the higher level tasks and kind of spending more time on thinking, designing experiments, evaluating data, and so on, rather than on, let's say, simple repetitive tasks that can easily be automated.
Yeah, I guess if you're working in the same kind of automation lab that I am, so a typical pharma lab with reaction optimization or maybe library synthesis, basically what's important is kind of the same thing, that you need to have a really solid knowledge of chemistry, of reactive chemistry, because if you're doing reaction optimization, then you know, the theoretical chemistry is what is incredibly important there. The literature can be really good. Sometimes for some reactions, it's not so good. And you need to be able to keep reworking your hypotheses. You need to be able to think in a slightly different way. So you're trying to come up with 96 experiments at a time, or, you know, 24. That's a completely different way of thinking than 1 or 2 or even 8 at a time. Actually, I would say, just on that, the thing we are looking for, or the thing I'm looking for anyway, when trying to hire people into these kind of labs, is partly an awareness that what we're doing is slightly different to bench chemistry, albeit theoretically the same kind of experiments. But the main thing definitely is being happy to progress, happy to change what you're doing, and happy to rework what you're doing. So if you've been doing something the same way for 20 years, that is great. But if something new comes in, then I really want to work with the person who, like, don't fix what ain't broken, but with the person who is willing to change how they do things to keep us progressing to the future.
Yeah, thank you. I think that's really important. I've got a question, another one for Nessa, actually. Back to you. I can't see who it's from, but I will ask it. Thank you. I've lost the name of who asked it. I'm very sorry, but I will ask it anyway. They say successful medicines notoriously take decades and cost tens of millions to develop. Do you see automation and robotics changing that significantly?
Somewhat significantly. I guess regulatory pressures are always still the same, but yeah, this is a really big driving force in both discovery and process chemistry. So, you know, you can make a ton of compounds in a clever way, in discovery chemistry. I think what's important there is the clever way, actually. So rather than just throwing everything at it and just making the stuff that you think you can make, which is kind of a downside of basically any form of chemistry, that you end up making the things you can make and not making the things that are more difficult. But, you know, if you have more chances, then sometimes that helps. It also helps if there's something you really want to make and you can use automation to optimize that reaction and make it actually work. I've done that so many times, even if it's something that's completely unprecedented in the literature. Same with process chemistry. We're really, really hoping that we can accelerate what we're doing and make it not just faster, but actually better than it would have been without automation.
Okay, that completely makes sense. I've got a question for Andy from Shruti. What's the most challenging aspect, in your opinion, when automating the tasks for researchers through robots? So this is looking at how the people are involved with the work that they're doing with the robots.
Well, I guess that's evolving, you know, as people develop more technologies. Initially, it was just the automation and making it reliable, but I'm beginning to think the bigger thing for the future might be the mindset and how to think in an open-ended way about problems. You know, you really do realize how much we do in research, which builds on making, you know, modifications to something reported in a paper, and it's very well defined, sort of, we're going to change the ligand concentration or something. If you ask people to think in a more open-ended way about what kind of 20, 30 variables should we emphasize in a search, it's actually very difficult. I mean, I find it difficult, and it's challenging. I think that's going to be I'm beginning to think that's going to be the most challenging thing in the longer term.
Right, okay. Felix, do you have anything to add to that?
I think that perfectly
that was perfect. That was the perfect answer.
I think like it's absolutely a change in the mindset. I mean, we don't think of it anymore. I think that kind of repeats what Andy and Nessa already talked about. It's like we don't think about a single experiment anymore, but we have to think in campaigns. Kind of what is the experimental campaign that we want to carry out? What is the search space that we're going to search through? Because I mean, chemistry is massive, and I mean, if we cite this chemical space has a number of 10 to the power of 60 to 10 to the power of 100 potential molecules. We can't, even with like a machine learning algorithm, we can't search all of that at the same time. And then if we think about conditions and whatever, that completely will explode in terms of dimensionality. So it's kind of the role of the chemist expert to figure out where in this space can we go, where can we start, where can we find meaningful knowledge, and how can we navigate from there? I think that is kind of an important question that is still something that's up to the chemistry researcher, to the expert that kind of runs the experimental campaign, and that's something that is something that we're not so much trained to and not so much aware of, but we have to think more in that direction.
We definitely still need the people. This is good to hear. I'm going to get back to more the kind of the nuts and bolts of things now. So I've got a few questions on how we're doing this. You know, people are obviously very interested to get involved. And a question from Nat, not me, another Nat. What is the simplest automated platform to start with and demonstrate the benefits of this approach? Now, I imagine this is kind of a big question with a small question at the same time. Anyone want to jump in and have any advice for that?
I mean, for me, it's literally an aluminium well plate.
Yeah,
like that's not an automated system, so I'm maybe not answering the question correctly, but actually that is the place to start. Like you can go really simple, you can do it all yourself. If you really do want a robot, then all I would say is make sure it will work with the chemicals you want it to work with. So a lot of the cheaper biology ones, I don't mean cheap like bad, I just mean they're less expensive than the chemistry ones, really can only deal with water, DMSO, ethanol.
Okay, so it's checking that, the chemistry you're doing is suitable with the robots that you're looking at. So you're saying that a DIY approach is possible, but and that is a relatively cheap way to start. But maybe, you've just got to check that what you're doing is actually going to work before you fork out all the money for these things. I'm going to come on. I've got a really interesting question. We've got somebody listening who's apparently not a chemist. They tell us they're an architect. and they're interested in lab design, which I think is a great question, because we've seen, and particularly from Andy's talk, you've got what were essentially, I think they were traditional labs that you've now added robots to, and they were kind of, not designed, I don't think, for having the robots in from the start, and now you've put robots in those spaces, but they are very much human spaces. Is basically the question. It's quite a long question, but basically we're looking at how are we going to change lab spaces in the future? Are we going to, are architects going to need to think about combining these technologies into buildings, and how's that going to go? I love this. It's a really broad question, but one for the future. Anyone can take that answer.
Yeah, I've been asked that one before. I mean, we've really worked on the paradigm that it needs to be a lab that's co-used by humans. I mean, if you have an HPLC, you still have to have a service engineer coming to service it, right? So if it's on the floor, that's a problem. So my feeling is initially won't change that much. I mean, you can think of some situations of like automated doors and so on, but I think my feeling is, unless you're going to build something like even the Stratios Cloud Lab that I showed, somebody has to walk in there and service it at some point. So I think initially it probably won't change much. It was also very expensive to build new labs. That's
definitely. Yeah, building a whole new lab is
others may disagree, but I think it probably slim times for architects. Maybe.
Well, maybe we should ask Nessa in terms of the industry side. I was just thinking, because obviously industry and the funding there works very differently to academia. So have you got a different kind of idea on this?
I mean, you see a lot of shiny, fancy buildings being used for robots in industry, and that's basically because the robots themselves are shiny and expensive, and you want to take all your visitors to see your fancy robots that are doing cool things. So, I mean, that's honestly the main difference that I've seen. I guess, yeah, I know there are a couple of people listening right now who are building their automation labs at the moment. And honestly, I think they tend to be quite similar to a normal lab, because in many ways they are a normal lab. It's just you need space for the robots in a way. It would be nice, maybe if you're designing all the way from scratch, if you were thinking to a future of having something fully automated to make sure that everything's kind of optimized where it should be for absolute maximum efficiency. So if you dispense your solids and your liquids, then you might put those in order and have a sort of like almost a production line type approach. But, those things take a lot of time. Anyway, you need to think about glove boxes, air-free environments, whatever it is that you want to use. Most automation labs actually do look a lot like other labs, just with robots in.
Excellent, thank you. We are really running out of time. I'm going to have really one final quick question from Ahmed. What's the biggest barrier towards automation? And I need a really short answer from any of you. But yeah, what do we see as the biggest barrier for moving forward in this field?
I think it's software automation and interoperability. I think that sometimes, you'll see people buying all the fancy robots and it's like, did you work on your data flow at all? Well, maybe not. So that's going to be a hindrance.
Felix is nodding his head and very much in agreement, I think, there.
Yeah, 100%. It's directly aligned with what I talked about earlier. I think we have to, at the point where we want to integrate robots into workflows, we need pipelines for addressing the robots, getting the data back out, and getting the data kind of in an interoperable fashion, and kind of really putting everything together, having the software that can control it and that can get the data, evaluate the data without bugging around with proprietary data formats. I think this is a very major aspect that we need, especially if we want to integrate robots into pipelines and longer, higher level workflows.
Mm-hmm. Andy, anything to add? You're nodding again.
No, not really. I think Nessa and Felix are 100% right. That is the short-term, mid-term barrier. Yeah.
Okay, brilliant. Well, oh my goodness, as usual, these webinars fly by with all these questions coming in, and we are at the end. And I'm going to have to say a massive thank you to all of our speakers today. I've learned a lot. I've seen a huge overview. And again, as we said, if you want to learn more, we've got a few articles in Chemistry World, and you can go to the website to find those, looking at AI and automation in chemistry. So thank you so much to our audience for getting involved in this conversation. Some great, fantastic questions for our panel. If you've enjoyed this webinar, then please do check out chemistryworld.com/webinars for future events. We've got a few webinars coming up. And while you're there, you might like to register for a Chemistry World account where you can sign up to our very popular Reaction newsletter that includes a weekly digest of big stories from across the world of chemistry. There will also be a really short exit survey after the webinar. If you have time, please just spend a couple of minutes to fill it in, as it really helps us to bring you the best webinars possible. Now, I'm Natalie Starkey. I'm Chemistry World Science Media Producer, and I look forward to seeing you again in a future Chemistry World webinar.